Hi guys, my name is Alexander Victor, and in today's session, I'll be walking you through data augmentation with TensorFlow and Keras. And make it very brief, and I think we should be done in the next, say, around 20 minutes at most. So if you let me, I'll be using Google Colab, and I will share my screen. And if you don't know how to access Google Colab, you can simply just go to colab.research.google.com. If you have a Gmail account, you should be able to access Google Colab. Now, in this class, we'll be using the Cassava Leaf dataset to perform data augmentation with TensorFlow and Keras. TensorFlow and Keras. So using dataset from Keras to perform analysis, and then we'll be trying to augment these data sets, trying to create new types of data sets from the particular data set that we have. It is very easy and interesting, and you get to see how this operates. In order to start that, first thing we need to do is to import all the libraries that are required. So to do that, we'll need to import the libraries that we need to perform the data augmentation. Now, Python comes with a lot of interesting libraries that helps in performing data augmentation. And for the sake of this class, we'll simply just adopt some of them and use them. The first one we would like to import is the matplotlib, which is a very important library that helps us to be able to plot or visualize our plots as in a better way that we want. The next thing we want to import is the NumPy. NumPy assists in data analysis for us to be able to store a large data frame. And in order for us to be able to use the data sets contained in TensorFlow, I'd like to import TensorFlow itself. Now, you must understand that TensorFlow has evolved since the first version was created, and it has been used over time, and it keeps getting upgraded with new module and new procedures that can assist in performing different types of analysis in machine learning. So we would be using a feature which helps us to import data sets inside TensorFlow called datasets, and then we'll call it TensorFlow dataset. And lastly, from Keras, we would be importing layers because we need to be able to frame our different images, which is the Cassava Leaf that is stored inside our Cassava Leaf dataset. We'll be using layers to be able to display them. The next thing we want to import Keras. So because these are just basic libraries, when we run them, it's basic. So it simply just compile all the libraries together and helps us to capture all the functionalities. The next thing we would like to do, because we have imported the data set into what we have right now, we would like to split these data sets into training data set, validation data set, and also the test data set, because when the model for performing the data augmentation is built, we will need to train it on a particular data set, which is called the train data set. And after training the data set, we would also want to test to see this performance as compared in comparison with the test data set. And finally, we would now validate it using the validation data set. So in order to do that, we can also still simply split them into, like I said, train_ds, which is a train data set. We have the validation data set, and we have the test data set. Now, our data set has been split into three, and then the next thing we want to do is call our data set, which we had imported from TensorFlow, which is TensorFlow dataset. So we want to pull out a particular feature from it, which is the metadata, the structure of the data set. So we pull out, we use metadata equals to TensorFlow dataset dot load. And our focus, because it has a lot of data sets stored inside it, we want to pick just a particular data set inside the TensorFlow data set, which, like I said, for this illustration, we're using the Cassava data set. Again, you could decide to use as many other data sets as you want, or check the various types and use them. But for the sake of this illustration, we'll be focusing on the Cassava data set. Now, having pulled out or loaded the Cassava data set using the command, the next thing we would like to do is split this data set into, like I said, the training data set. Now, in splitting our data set, we could decide to split the data set in different sizes. So for the sake of this training, this illustration, we'll split our data set into 80% for the training data set, and maybe the last 10% each for validation data set and also test data set, because we need a lot of data sets for us to be able to train our model to perform effectively. So we pick this particular data set, and then we say this is taking data from 0 to 80. And after we've decided that, we can decide to say, okay, we have 0 to 80. Then for the other data set, so we have the validation data set. Let's take the validation data set. It's taking data set from 80% to 90%. And lastly, we have the test data set. So the test data set takes values from 90% to the test data set takes data set from 90% to the end, which is of course to 100. So 90% to 100. All right. So now we have splitted our data set into 3. We've taken it from 0 to 80 and from 80 to 90, which is 10%. The remaining 10% is from 90 to 100%. Now, in order for us to be able to see what information is well stored inside it, we use the with_info. So we want the information to be clearly displayed for each of the data set we are selecting. And then we also want it to be as a supervised data set, which in this case we say supervised equals to 3. Having splitted our data set, we can simply proceed, because we know that definitely this data set will be splitted into 3. The first one will be assigned into the training data set. The next 10 will be assigned into the validation data set, and the next 10, the last 10 will be assigned as well into the test underscore data set. Because we have this data set which has, we already have our data set. Now we want to capture it alongside the label. So it means being a supervised learning model that we intend to develop, which has a data set that is already structured into these 3 categories for training, test, and validation. The next thing we want to do is try to capture the labels of these data sets so that it comes alongside with the label. So we go with data number underscore classes equals to metadata dot features. All right, so then we are interested in calling out the label of the data set. And this is equals to those classes. So we have num.classes. And then the goal is to print num underscore classes. So we'll get to see the number of labels that are going to be captured inside these particular, based on feature selection, the number of labels that will be assigned to the various data sets that are stored inside our Cassava data set. But because it's taking time to complete execution, I'll just proceed into explain the other sections, and then we can come back to executing the subsequent code. So this line right here will produce the number of labels which are potentially going to be assigned to the data sets that we're extracting from the TensorFlow dataset repository. Now, having defined that, the next thing we want to do now is visualize our data set with their label. So we want to check and see. So we have data, we have num, dataset info object features. Okay, the spelling, we have an error there. So we have 5 labels that are possibly going to be assigned to the various data set that we have decided to select in this case. The next thing we want to do is visualize our data alongside the labels that we have identified. So we have get label name equals to metadata dot features. So we are calling out the features of the label. So the label feature, and then in this case, we pick in to string. So it means we are converting it from integer to string. So we have in case we have the label defined as an integer format, we want it to change it to string. The next thing we have, we want to iterate the train data set. So we iterate, we say train iteration equals to iteration of the training data set, the iteration of the training data set. All right. The next thing we want to customize the plotting functionality. That's the figure. How the figure will be displayed, the size of the figure. So we have fig size, which is equals to 12,16. That's basically depend on we want about 12 images to display on a single row of different sizes. Then with the next thing, we want to pick up a range in that list of 12 images, and we want them to have different features as they display. So we have range of 12, and we have image, label. The image comes with a label, and the next image. So it means it keeps picking up different iteration from the training data sets, with each having an image and a label side by side with it. So having done that, we want to now add, we want each image to be displayed on the same plot as a subplot of the previous plot that has been plotted. So we have subplots, and we have one column, 12 in one row. Then they should align one after each other. And after doing that, we just, of course, we want the image to show. So we use image show and not the usual plt.plot or the show. So we want image show, and we want the image to show alongside with it. And because we don't want it to actually, we want it to just plot it out without actually capturing the axis, we can simply turn off the axis. So we say plt.axis. plt.axis, because we don't want the axis to be on, so that it doesn't like have the X and the Y scale in the axis structure. And lastly, we can simply now say plt.title get label. So this is going to help us label each of the image or each of the images with the label we had defined previously. So we have here, and we had defined our label from this section. So then we have known that we have 5 different types of label. Now we are calling that label here. We are converting any label that is a string data, that's an integer, into string. And then we are assigning it to all the training data set we want to display. And then we are picking just 12 out of that selection. So we'll run this right now. It's, okay, it says here that we have an error. So let's look at it again. PLT title get underscore label underscore name. And then we have label. And then we have, I think, the full column there. So when you run this right now, you can see the cassava leaves will be displayed. And you can see clearly that we have 12 of them outlined here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you look at this clearly, you can see the types of label that it has. Number 1, it has the CMD, the CGM, healthy, and then CBSD. And then you have 1, 2, 3, 4. So if we increase the number of images that we want displayed, it's going to display all the 5 different labels that exist But for the sake of this example, we just want to have 12 of them displayed. And if we want to increase it, we can just simply come to this line of code and change the number of images that we want it to display, and to automatically increase the number of images that we want displayed. Now, having done that, we can decide to continue extending the iterations. We can make it to work on the training data sets. Okay, we've seen it work on the training data set. We can also try it as well on the test data set. So in order to save time, I'll just copy out this code and just take it to a new cell, and then we can just run the test data set. So in order to run the test data set, we just need to change the data sets here. So we can do, instead of train, we just run the test data sets, and we also call this test iteration, test_iteration. Now, if you run this as well, you can see that to seamlessly display the test data set. So you can see that the test data set has been iterated, and we've seen the images for the test data set and the training data set. You can see it can look a bit much different because they all contain different types of data set. And if we decide to proceed further to evaluate that of the training data, the validation data set, we can simply just add a new cell, and allow me to still also copy and paste that line of code. And here we can simply just say the validation data set and also include validation here. And we can also change this to validation iteration, and the same thing. So it lists for us every data cell that is augmented and stored inside the validation data set. Now, having done that, we have been able to split our data set into the test data set, the training data set, and the validation data set. And we've also been able to view all the various data stored into each of these data frames that we have created. In terms of data augmentation for the Cassava Leaf, we can decide to perform different types of augmentation. One of them could be rescaling, another could be resizing, and we can also decide to randomly flip these data sets or rotate them, or even increase or reduce the contrast of the data set. So for the sake of this class, we will first start with resizing and rescaling our data set. In order to resize our data set or rescale it, the first thing we need to decide is the size of the data set. So what size do we want each of the image that we are resizing to take? So here we say we want it to have an image size of 180. And then the next thing, we want to define a resize variable. So we want it to resize and rescale. So we want a resize and rescale variable, which in this case uses a function which is stored inside Keras, which we call the sequential. And the sequential is a layer or a procedure which is stored inside Keras, which helps to be able to define a sequence or a sequential display of whatever data that we are performing an optimization or the data augmentation on. So in this case, we simply call the sequential, and then now we have layers. Recall that we have imported layers from Keras in the past, so we have to pull it up. And if you see, we have resize that is stored as a feature inside layers. So here we call it resizing. And then because we are resizing, we want to resize based on the image we have defined. So we have the image size. We can decide to either put 180 there, or we can simply just put image underscore resize. So we want it to be height and width of 180 by 180. So in this case, we can simply call that resize, resize. And next one is layers. So we've done for resize. The next thing is rescale. So we call this rescaling. So we want to rescale it to 1 by 255. So in this case right now, we are trying to change the structure to give it a new scale over a range. And then we want the range to go from 0 to 1 or from 0 to 255. And now we put that up together, it is 1.255. Now, having defined the augmentation measures or procedure, which is to rescale and to resize, we want to see how that affects or impacts our image, which we are intending to augment. So we call that result equals to resize underscore. Because we have defined that resize and resize and rescale, we simply decide to say, okay, we are putting an image. So we want to resize and rescale an image. And therefore we have plt.axis. Again, we want to turn off the axis. All right, so we want to turn off the axis, and then we want to now view it. So we say image show, and then we want to view the result in this case. So we want to view the result. So when we run this, it's going to, first of all, pull out the image from our data set, and then it's going to resize it and rescale it compared to how it originally is. Now, what normally happens in this case is that if you look closely, the last data set here under the validation data set is the same thing that we are having here in this case. The only difference here is that it picks the last data that was displayed in the last iteration, and then it has rescaled it and resized it. You see, the first thing is that the scale has changed. Also, the size has as well changed. This is what we are working with the last CMD here. If I try to run this iteration again, it will change. Of course, it's going to change the output. Okay, still remains the same. But if, for instance, we have more data, and it's because we have fewer data stored inside the validation data set, which is why this is not changing. And if I was reiterating either of the ones that for the test data and train data set, we'll have a different image. But the point we're trying to make here is that that last image we're looking at here, which is at CMD, has been resized and rescaled by 180 by 180. It has been resized by 180 by 180, and it has been scaled from 0 to 1 and from 0 to 255, which is why you can see the image look a bit different. Now, this is a new image that we have created from an existing image. This image was created by simply rescaling and resizing an existing image. And that is one job of data augmentation. So data augmentation creates a synthetic data and use that to provide new sets of data that never existed in the past, and is able to use them. So for instance, if we have, say we have 100 data points of data set, and then we need 1,000 data points, we can decide to augment that data set and increase it from 100 to 1,000. And that is the whole goal of data augmentation. The next thing we want to do as well, we have been able to perform resizing and rescaling. We can decide to flip or randomly rotate a certain image. For instance, this image that we are seeing at the moment, we can decide to flip it. We can decide to rescale it to produce many more different data, or the Cassava Leaves data of this very feature. We can create it with different features. In order to do that, I will just simply create a variable called data augmentation. So we call this data augmentation equals to keras.sequential. Recall that we are still using the sequential feature here. And in this case, we simply pull, so we have it as, okay, we have this. And then first, we want to recall layers, which comes from sequential, from keras, so layers from keras. And inside layers, we have different types of procedure. Here, we're just trying to pick random flip. So we just want to pick the feature of random flip. So we have random flip. And then in this case, we're deciding what type of flip we want. We want it to be a horizontal, and vertical flip. Horizontal and vertical flip. Also, we want to also pick we also want to rotate that same image. So we have layers dot random rotation, layers of random rotation. So once after we have flipped the image into horizontal and vertical formats of different types, we also want to now rotate it at a certain rotation ratio. So in this case, we are picking 0.5 as the rotation ratio. Now, having defined the procedure like we did previously, we can now define how we want it to print the number of images we want, so that we can be able to see the impact of the horizontal and vertical flipping And also we can be able to see the impact of the random rotation. So we have PLT figure. In this case, we have it to be fig size as usual. Now here we're trying to define the size that the figures should have. We can say 7,8 because of the number of figures that we want displayed. So we probably will just pick a few sets. So we have I in range. We can decide to pick any number. So let's say we pick 6, and then we have data. So we have augmented underscore image, which is equals to our data underscore augment, data underscore augment of image. If you look closely, the procedures are the same all through. The only thing is just changing the various features you want it to have at any given time. So we have PLT, the subplot, and then we have one image at any given column, 6 images in a row, and one image should come after the other. That is what this next line is. So it means you should plot one image at every column, 6 images in a row, and one image after the other. After doing that, then we need to now show the image. So we have in show. So we want to show the augmented data. So we have augmented underscore image, and then the numpy. So because we didn't rescale it in the previous line of code, we can now come here and rescale it like we did in the previous code. And don't forget to turn off the axis. So we have PLT the axis off. So in this case, we turn off the axis. So let's see what the outcome would look like. So when we do this right now, you can see clearly it gives us different images. So clearly it has this image that has been flipped in different formats. Now, if you look at this clearly, let me increase the size so we can have something to work with. Let's increase the size so we can have something to look at. So clearly, you can see that this image has flipped a bit compared to this, and it has flipped. And the rotation axis is just 0.5. So the flipping is not happening very, very large. It's just, moving at 0.5 ratio at every given time. So the image has changed. So in this case, we have several types of just a single image. So we have augmented, we have increased the number of images that exist just for one particular image. So imagine we're doing the same thing for all the images we have selected for this analysis. For instance, if the Cassava Leaf data set is about 1,000 and we augment all the 1,000, say for instance, in this number, maybe with a range of around 300, because if we change the value here to say 10, we're going to have 10 of that, starting from 0, 1, 2, 3, 4, up to 9. But of course, because this number, so in that case, we have to change this to 10. We have to change that to 10. So the point we're making here is that data augmentation helps you to recreate new sets of data that you don't normally have from an existing synthetic data that you have. So it's like helping you predict data set in the future. And if you come back to, in our next class, we're going to look at how to ensure that these predictions are accurate. So we're going to try to perform prediction and compare the accuracy, precision, and recall to be sure that the prediction of future data from an existing data is as accurate as it seems. Having done that, we could also perform other further evaluation. And one last experiment I would like us to try before we call it a day from this data augmentation using Keras and TensorFlow is increasing and reducing the contrast of the image. So for instance, we can still call this data augmentation. So we have data augmentation. You can call it whatever you want to call it. It doesn't have to be the same word. So you have keras.sequential. Recall that we keep using keras.sequential. And here we have layers.random contrast. Layers.random contrast. So here we have We want to have this image being displayed with a contrast of a certain degree. And in this case, we just pick, say, around 0.9. So we have the procedure defined. And after we've defined the procedure, we apply it as usual. So in order to save time, I would just simply move this whole text here, and then we can just execute quickly and see how it displays. So here we have, okay, so I'm going to take this out. So let's take out this again. So let's have this, and then we have the results here. So we have this image, and then we have data augmentation. So we have to just change this augmentation, image, by plots, and then we have that. So if we run this right now, it's going to display the image with a much deeper contrast. You can see each of the same image we have previously, but all having an alternating contrast from each other. This one is being dimmed up a bit. This one has been made brighter. This one has been made dimmed a bit. This one has been made brighter. And it goes on and on like that. So it has been randomly contrasted. So you have random contrast features applied to this data set. So this is one way you can be able to perform data augmentation using the TensorFlow and Keras. You can see how we're able to move. The first thing we did was to use TensorFlow to bring the data set from TensorFlow. So the TensorFlow contains a large chunk of, is a repository of a large chunk of procedures and data sets. So we pulled out our data set from TensorFlow, and then we use sequential as a feature and layers as a feature that is stored inside Keras to be able to perform all of these data augmentation. So I believe you've learned something. We'll see you in the next class, and we will explain further on how to test the accuracy of prediction using all these approaches. Thank you.